Let's work through Activity 5, where we get practice making predictions, making transformations of variables, and checking assumptions. So for this data, we are going to load in the bulldozer dataset, which records the selling prices of bulldozers that are sold at auction. We're interested in predicting and studying the relationship between selling price and various quantities. And we're first going to start out by looking at the relationship with the usage, the number of hours of usage of the bulldozer. So just a quick reminder, if you ever have any questions about the data sets that are built into Reg class or any of the commands that we use for Reg class, you can always do a question mark and then the name of the command after you've loaded up library reg class. So I'm going to load up library reg class right now. And if you did want to know something more about the bulldozer data set, then you can just type in question mark bulldozer. And what it will do is it will tell you how many observations are in there, and then go down and talk about all of the variables that appear in the data frame. Whether or not the variable is numeric, if they're categorical variables, factors, etc. And you can always learn about that. One important thing is you never want to have the question mark command or question mark data set in your R chunk, because that'll cause some really weird behavior, so just type it down here in the console. All right, so we are going to load in the bulldozer data set. And question number 1 asks us to make a scatter plot of that relationship using plot. And in this case, modifying it to add in some additional arguments to make the plot a little bit prettier than it maybe normally would be. So what we're going to do is we're going to make a scatter plot to see this relationship. And in this case, we're interested in predicting sale price from usage. So I know my y variable is sale price, so y twiddle x. Usage is my x variable. And then I say what data the variables live in, bulldozer. And I'm just going to add in PCH and CEX equals 0.3. All right, so when we gotta actually run the data bulldozer command, load that up. Now it's inside. Now I can actually make the plot. All right, so here's our relationship, and we'll see that the relationship doesn't look very strong. I don't see much of a pattern at all. I don't see much of a trajectory of the stream of points. It looks pretty flat here. But, you know, there's no curvature. There's no obvious curvature here, so linear regression is an appropriate starting point, at least, to try to model this relationship. The vertical spread's about the same everywhere we look. It's hard to tell what's going on here, so we can kind of ignore that. But for lower values of usage, it looks like that points are scattered up and down by about the same amount everywhere. So it does look like linear regression is a good first step for looking at this relationship. And just, by the way, if we didn't have those two arguments, this is what the plot would have looked like. Kind of messy, too many points to really see. And so that's why I said, hey, add in those two extra arguments. PCH makes the points filled circles instead of open circles, and CEX makes the points smaller than they normally are. So any number less than 1 makes them smaller. All right, so we fit the plot, and now what we want to do is we want to fit the regression model. And so by default, I'm going to name my regression M. You can feel free to name it whatever you want. And the syntax for LM is the same as the syntax for plot, for associate, etc. So let's go ahead and fit that model. And we're going to add the regression line to that plot, which we know we can use abline to accomplish. So there we go. There's our relationship, and we see that it's actually somewhat negative. That makes sense. Bulldozers with higher usages, probably should be selling for less because they've been used more, and so it looks like that the line of averages, our regression line, is confirming that intuition. All right, so one thing we know about the slope, the intercept, p-values, confidence intervals, etc., they're only reliable. The numbers only make sense when linear regression does provide a reasonable reflection of reality. So we always need to check the assumptions of our regression model to make sure that that's actually the case. Now I've written a command called check regression, which will go through all of the aspects of the analysis for us here. So the first thing that we do is we actually look at the statistical tests for the assumptions. Now the statistical tests are of limited use because we know going into this that our model is wrong, and so when we fail the statistical test, that's really not telling us anything new. We just got to make sure that the model isn't too wrong to use. However, if we start out with the statistical test and we find that we pass all of them, then we're good to go. We know that our model is reflecting reality reasonable enough for us to use here. All right, so in this case, what we do is we look at the p-values and we notice that they're all less than 5%. All right, so that's bad news. We've failed the tests of the assumptions, meaning that from a statistical point of view, the relationship isn't quite linear. From a statistical point of view, the vertical spread isn't quite equal. There's some heteroscedasticity. And from a statistical point of view, the distribution of residuals isn't quite normal. All right, but with so many data points, we kind of expect to fail these assumptions. We just have to make sure that the violations aren't too severe. So we go and we check the residuals plots to see whether or not that's the case. So to check for linearity, we look at the residuals plot and we look for signs of any leftover curvature. Anything kind of an overall pattern that's maybe a U-shape, upside down, or right side up. And in this case, I don't see any sort of curvature whatsoever. It's pretty much just a flat horizontal band of residuals here. And so whatever violation that test is picking up on must be fairly small, and in this case, inconsequential, and I can ignore it. All right, well, what about vertical spread? We failed that test. And what I want to check for is in the residuals plot once again to see if the typical size of the residual, the amount of scatter up and down above the horizontal line here, if that's about the same everywhere. Now, it's hard for me to gauge what's going on here on the left, so I'm just going to focus on where there are a bunch of points. And so I see that, okay, it does look like the vertical scatter up and down. The typical size of the residual is about the same regardless of what the predicted selling price of the bulldozer actually is. So I would say I would pass that test actually. Whatever violation the statistical test is picking up on is fairly small and inconsequential. And the last thing I have to address is this failure of the normality assumption. So I look at the QQ plot here, and this QQ plot looks actually pretty good. What we're looking for are signs of systematic curvature away from the line of perfect concordance, the diagonal red line here. And we see that the vast majority of points actually fall pretty much right on that line and within the upper and lower dotted bands. We do see a little blip away on the left and the right, but that's always going to happen actually. It's almost impossible to have a perfect match here. And so I would say that this violation is actually fairly small. I notice that there is a violation because not all the points are inside the upper and lower dotted bands, but this is a relatively small and inconsequential violation for this many data points. So which of any of the tests are passed? Well, they're all failed, since the p-values are less than 5%. So we did a sanity check, and what we see is that there's no hints of curvature. So the linearity assumption looks okay. Equal spread. There was no hints of heteroscedasticity. So the equal spread assumption looks okay. Typical size of the residual is about the same everywhere. That's good news. That's one of the key assumptions of our model that allows us to trust the confidence intervals and prediction intervals. Normality, we do see some systematic bend away from the diagonal line at the left and right of the plot, but this almost always happens. So this kind of violation is relatively small and inconsequential. It's only if there's a global pattern like we've seen in the notes that we really worry about the normality. They're just a little bit outside the lines here. All right, so like I say, in my opinion, and it really does take quite a few years to really build up the intuition to make these sort of judgment calls, none of these violations are severe enough to invalidate the model. It looks like it provides a reasonable enough reflection of reality for us to actually use. So there's a neat command called visualize model that allows us to study the regression line and the confidence intervals and prediction intervals if we're going to use the model for predictive analytics. So visualize model M. And what visualize model does is it shows you the scatter plot with the regression line in red and the 95% confidence intervals with the solid black lines, 95% prediction intervals in the dashed lines. Now notice the legend is kind of in an inconvenient place. It's covering up some stuff, and so there's some flexibility in where we put that. I'm going to add in an additional argument, top right in double quotes. That's just going to move the legend over here. Okay. So, two types of predictions we might be interested in making. One for the population average, the average selling price of all bulldozers with a usage of some particular value. And those 95% confidence intervals for the population average are the upper and lower solid black lines. If we were interested in predicting an individual bulldozer selling price, well, their 95% prediction interval is given to us by the upper and lower dotted black lines here. Okay, so one thing that we can do to check to see if our assumptions do seem to be reasonable enough, and we saw that we passed them with the residuals plot, but one additional sanity check is that if the model is a really good reflection of reality, then by design, 95% of the individual observations should be inside the 95% prediction interval, because we say there's a 95% chance that a bulldozer is going to have its y value inside the upper and lower prediction intervals here. And is that the case here? Well, how many should be outside the upper and lower dotted bands here? Well, there's 924 observations, and so if I said that 95% are supposed to be inside, that means 5% are allowed to be outside. 5% is about 46, so about 46 should be outside. Now, how many do we see? Well, we see a few. Maybe 1, 2, 3, 4, 5, 6, maybe. Maybe that's off by a few, but there's nowhere near 46 here. So we observe much fewer than 46 here, about 10 or fewer even. And so what this indicates is that, okay, there is a bit of a mismatch between what our model is predicting for the relationship and what reality actually is. No huge surprise, the real world's more complex. And it looks like in this case that our model is overestimating the amount of variation in sale price. If the model's doing its job, then 95% of the observation should be inside the upper and lower dashed bands here, the prediction intervals. The fact that fewer points are outside indicates that the model thinks that there's more uncertainty going on than there actually is. So these prediction intervals actually could be a little bit closer to the regression line. It can be a little bit narrower because we're allowed to have a few more points to be outside these bands. All right, so the model is overestimating the amount of uncertainty. Actual selling prices are a little bit less variable than what the model is predicting. And that's not really a bad thing. Our model's a little bit conservative in this case. By design, there's a 95% chance that the point should be inside the 95% prediction interval. And it looks like in this case, we're doing a little bit better. There's about a 99% chance that they're inside those intervals. We'd like those two numbers to match up, 95% to 95%, but if anything, we're happier to err on the side of caution, have our intervals be a little bit too wide. So there we go. All right, so the prediction intervals appear a little bit wider than they need to be. Let's go ahead and just make predictions based on this with that in mind here. So to make predictions in R, it actually requires a little bit of work here. The first thing we have to do is to define a data frame that contains the x values that we want to make predictions at. So in this case, what I'm doing is I'm defining a data frame called 2.predict, left arrow, I'm defining it here. And this is how I create a data frame. I write out the function data.frame, and then in parentheses, what I do is I give the name of the column and then a list of values that I am going to be putting in the data frame. So in this case, this data frame is going to have a single column called usage and 3 values, 0, 10,000, and 30,000. All right, so with that data frame defined, let me run that command. Then I can use R's procedures to make predictions. So first thing I want to do is to make 95% confidence intervals for the average sale price among bulldozers. So I want to predict the population average in this case. And the way that I'm going to do this is to use the command predict. I give it the name of the model that I'm going to be using to make predictions, and I named this M earlier on. And then what I'm going to say is I want to say interval equals, and then I need to specify confidence, because in this case I want a confidence interval for the population average. And then what level of confidence do I want? Well, I want level of 0.95. Okay, so when I run this command, what it will do is show me what I didn't actually want to see here. It made predictions for every single data point that went into building the model M here. I actually just want my prediction intervals on this the values of usage in my toPredict.data frame. So I forgot that I needed to add this additional argument, new data equals to.predict. By default, it'll make the intervals for all the points in the original data set. I don't want that here. Okay, so use the regression model that we fit to make predictions on this new data in the to.predict data frame. Make confidence intervals with 95% confidence. So we'll run that, and on the far left column are the point estimates, basically the values that we would get out by plugging in usage into the regression equation, and then the lower value and the upper value of the 95% confidence interval. So in this case, for a brand new bulldozer with a usage of 0 that corresponds to the top row here, I would predict that the average selling price is about $79,500. And there's an uncertainty about that prediction. I'm 95% confident that the average selling price would be between about $75,600 to $83,400. Okay, so that's great if I want to just predict the typical selling price of bulldozers in general, but most likely I'm going to be using this model to make predictions about a particular bulldozer that might just be coming up for auction. And so in this case, I would like 95% prediction intervals. Prediction intervals are for individuals, confidence intervals are for averages. So how would I do this? Well, just a small modification of the code I just wrote. So interval equals prediction. And so when I run this, same point estimate, because I get the same estimated value just plugging in usage into the equation as I did for the average. But you'll notice that the 95% prediction intervals are phenomenally wider than the confidence intervals for the average. Predicting an individual is a lot harder. Who knows how far off the individual is going to be from the average value? That's a random amount. So these intervals, as I saw with visualized model here, are a little bit disappointing, or a little bit wide to be all that useful. For a brand new bulldozer, I would say there's a 95% chance that it's going to go for between $12,800 and $146,000. That's a huge range of prices. I've hardly narrowed it down. But there's nothing I can do. That's just the nature of the variability in sale price at any particular value of usage. That's just the way the world works in this case. I've done my best with the regression model to make predictions, and there's not much else that I can do here. All right, so let's move on to a new relationship. Let's look at the relationship between the sale price of the bulldozer and the year in which it was made. Now, we've looked at this example a few times in class, so let's go through it more formally here. Here's this relationship. I don't like those points, so I'm going to make it solid circles and make those points smaller by adding in those additional arguments. And I see that there is probably some sort of curvature going on. So, all right, maybe this is not a great candidate for a relationship to be modeled by a regression. So let's go ahead and fit the model and check some of these assumptions. So I can pretty much just copy and paste. The syntax for plot is the same thing. Rerun that model. And let's check this regression. Let's check the assumptions here. All right, so we first start out by checking these tests, because if we pass them, then we're good to go. But not a huge surprise, we end up failing 2 of the 3 tests here. With so many data points, these tests are very sensitive, even when the violations are small and inconsequential. So I'm failing the test for linearity, and I'm failing the test for normality. I actually passed the test for equal spread, so I don't even have to look at that on the plots. So I failed the test for linearity, and my eye is drawn to what looks like kind of a dip in the residuals plot, some sort of curvature that I'm not all that happy about. And with the normality assumption, a huge red flag is raised here. Notice, in this case, all the points are actually inside the upper and lower dotted bands on the right and the left. But I have this weird little dip here where we have a ton of points that are actually outside the upper and lower dotted bands, indicating there's some systematic departure from a normal distribution. And in fact, what I think is going on in this histogram here, here's the red normal curve, and we see kind of an excess of residuals right here. Too many residuals at having these negative residuals here. Weird, I don't know why, but indicating a systematic departure from normality. I'm uncomfortable using this regression model. So let's try to fix it. Maybe there's some transformations of the originally measured variables that do have a linear relationship. So let's try this. Find.transformations is going to take our fitted linear regression model and then go through and try to come up with something that's better. So what it does, and there's a lot of output here, too much output really than I need. We have Y being sale price, X is year made, and it says, all right, if you didn't use any transformation, your R squared would be about 54%. Now, if you do use a transformation, you can do a little bit better. Notice that if you instead have your X variable be year made raised to the 1.75, and your Y variable be sale price to the 1/2 power, the square root of sale price, your R squared is a little bit higher at 55.3%. Now, 55.3% versus 54.3%, not a huge difference, but we do a little bit better. And more importantly, if we look at these transform variables and we find a relationship that's better modeled by a linear regression, we're a lot more comfortable using it. We saw we had issues with the original variables. We don't want to use that model anyway. So here's some plots of the original scatter plot and then what it looks like with the 3 transformations that yield the highest R squared. Not a huge difference here, but maybe a little bit more linear than what we had to begin with. So let's try to see if we do any better by using these transform variables. So this technique doesn't always work. It doesn't always save the day here. So let's see if it works in this case. So to fit the transform model, I need to define my transformed x and y. So in this case, I'm taking my x variable and raising it to the 1.75 power. And so I need to refer to that x variable, the year made, by saying, all right, bulldozer, $ year made. That's how I extract that column out of the bulldozer data frame. And I'm going to wrap that in parentheses and then raise that with the caret sign to the 1.75. And then for the transform y variable, well, I need to extract the sale price and then raise that to the 0.5 power. All right, so I'm going to fit a linear regression with these variables. And so I'm going to call this m.trans for transformed. And I'm predicting y trans from x trans. Okay, so how do I do? Do I fix this regression? Does the model look okay after the transformations? So boop, 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 boop. Fail all the tests. Not a huge surprise. Once again, a lot of data points. Do I see any issues? Well, yeah, I didn't really fix the regression at all. I don't necessarily see any non-linearity now here. I don't see any sort of obvious U-shape. I don't see any obvious signs of unequal vertical spread. I don't have too many points over here to gauge how spread out the residuals are up and down, but it looks like they're roughly about the same size no matter where I look. But I do have this ugly, weird kind of systematic curve above and then immediately below the diagonal line in the QQ plot. And that indicates a problem here. So, all right, we tried our best. Sometimes this procedure works, sometimes it doesn't. And in this case, it does not appear that we can model the relationship between the transformed quantities with the linear regression. There is still a painfully obvious violation of the normality assumption. Some weird curvature on the left. Though the linearity assumption and equal spread assumption look okay. So we tried our best, we failed. That's all right. Not all relationships can be modeled with simple linear regressions. There are ways to approach this from a completely different angle. We'll get that. We'll cover that at the very end of the course. But there we go. So we are done. Let's make sure that this knits. And just as a reminder, it's always good practice to go back and edit your final work after you've knitted it. And in this case, some of these plots are really big, so I'm going to say, let's make that smaller. Let's make this smaller. And just have, the comments match up in appropriate places. I don't need to copy and paste that advice. Let's see if I can make this even just a little bit smaller to get all these comments on there. Maybe increase the margins a little bit. Oh, too much. There we go. That's a huge scatter plot. I don't need it that big. And that looks fine. That looks fine. And maybe I'll insert a page break here. Make this scatter plot not quite as big. make these plots not quite as big, and don't need that advice. I'd like to get the results of those tests up in that page. That looks good. Transformation plots don't look that great. Oh, look at all this ridiculous output. Let's delete a lot of it. We don't need all that much stuff. Let's just put in the top few transformations. In fact, notice all these are 0.553. There's really no compelling reason to choose one versus the other. They all do about the same. Let's insert a page break here. Let's make these plots smaller. And let's take away that advice. And there we go. We have our final solutions.